Okay, so where do you want to start? Here is the review sheet.
The line of the regression ANOVA output, is there one specific line for that?
You just mean like
regression?
cells.
Which one are you talking about?
Question 1 of 1.
It's the FP value.
FP value? Okay, okay.
In order to test the null hypothesis that all of the betas are 0, that's the overall F-test per model. So which line of the regression ANOVA, that's the model line, the top part of the ANOVA table.
Okay.
Right? And what is the alternative hypothesis?
At least one of them is not equal to 0.
Would you write that H of A is B sub J does not equal 0?
Yeah, you could do that. B sub J is not equal to 0 for at least one J equal 1 dot 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 up to K. So one of those J's, you're not getting a 0 in there. At least one of them. All right?
We can just write at least one B sub J.
Yeah,
is not
you
equal.
could just write it out in words. At least one of them is not 0. What about number 2? In a multiple regression, interaction exists when? Which of those is the definition of interaction? They kind of all say something similar, so it's a bit subtle, but I heard B. Well, let's read that one. The relationship between the mean value of the dependent variable y and one of the independent variables x1 changes in a meaningful way at different levels of another independent variable. That sounds right. So what's wrong with C?
It says is no longer statistically
It's
significant.
no longer significant when. So that's saying if you put x2 in the model, the significance of x1 goes away. That doesn't have to happen. Sometimes it does with interaction, but
Is C like the situation with the hand and the wingspan thing?
yeah, C is
The
yeah,
hand didn't explain
yeah.
any more than the wingspan.
Right. But there was no interaction between wingspan and hand. Right? Yeah, and A just says it changes when you put that variable into the model. Right? And that's not quite right either. Okay? Anybody wondering about 3? Or is that one fairly obvious?
Is it C?
It's C. R squared will get bigger when you add another variable to the model. But the second part is what's wrong. Unless the variable is negatively correlated, in which case R squared will decrease. R squared never decreases when you add another variable.
Right, and it can't increase negatively. Sorry. I remember seeing somewhere negative R squared, where it was where in a linear relationship it went down. Like the slope of y was not the slope.
If the
of y.
slope of the line is negative, you'll get a negative R. If there's one
Negative R,
variable,
that's it.
you won't get a negative R squared.
Okay. That's where I was getting tripped up. Sorry.
Any problems computing the adjusted coefficient of determination?
Do you have the answer? I computed it.
I-
177.
Yeah, that's what I got.
Okay. I've loaded up the key, but I don't think I've finished it yet. Apparently I haven't even started it yet. So the key will be out there sometime in the next day. It may not be today. How do you compute adjusted R squared?
1 minus MSE over MST.
1 minus MSE over MST. And MST, we're not used to seeing that in an ANOVA table, but what is MST?
That's what you do out of
Sum of squares T divided by n minus 1, which is the degrees of freedom for total. Okay, and what'd you say the answer is?
0.7778.
7778. All right. Any trouble with the matrix algebra ones? In order to work, if I put one like this on the test, you want to make sure you have your TI-84 calculator with you that'll do the matrix operations. And it'll be a real small little matrix like this. And everybody knows how to do that? Don't need to go through it?
Because that's just when you do the, like the x prime, whatever, x prime x inverse, that,
Yep.
okay.
Yep, so the solution, we can go ahead and write in matrix algebra what the solution is. The matrix algebra solution for the vector of parameter estimates b. So b is equal to what? What do you do?
X prime x inverse times x prime y.
Right?
And I guess on this, because this is assuming that our x is still, didn't the book do it different because they changed what x prime was? Or was that on?
No, that's for a single observation.
Okay.
That's to get the hat value for a single observation, the distance value.
Okay.
Right? This is the, these are all matrices, not vectors. That's all the X matrix. Right? So what is the X matrix from this? What would you do to get the X matrix?
Put a bunch of ones in the y column.
Right? You add ones as your first column, and then these two columns. That's going to be your X. So you can take the transpose of that times X and so on.
So that's all you would want us to write down for B, is just all the ones and the x's. For B is the write out the x matrix.
Yeah.
Write out the X matrix, yeah, for the model. Yeah.
So there'd be 4 ones, x1, x2.
Yep.
If you just look at
So the X matrix is that.
The part A, right at the general multiple regression model, is that just Y matrix equals X matrix times B matrix?
Yep.
Plus epsilon matrix?
Y matrix equals X matrix times the beta matrix, matrix times, or plus the epsilon matrix.
Tricky.
So that's A.
Okay.
Oh, you know what? I think on part C, all I'm asking for, I think this is the answer. I wasn't asking for,
So you're leading us along to do part two.
yeah. And
Part
when
B is-
I originally had this as a test question, I had part E, which then gave me the solution to this, but decided that's too much work. So then I just stopped at getting this part of it. All right, next question. Any questions about this one? This is number 6.
Yeah. What's the answer to A? Is it just ST and AT?
Using the above matrix, which variables seem to be good predictors of evaporation? Base your answer on the correlation values and the p-values provided. So, we've talked about this matrix out of SAS, right? So you know which ones are the p-values? Right? P-values are the ones down below. Right? So if you look at good predictors of evaporation, you want to look only at this top row or the first column. It's a symmetric matrix, so so this one looks to be strong, this one looks to be strong, the other two do not.
Then why do they take out wind only in the second part?
Say it again.
Like they leave in.
Part B or something?
Yeah. Then when they ran it, they only ran ST, AT, and H. They never ran wind.
Because when they take out one, it changes the model, doesn't it?
But why wouldn't they take out H2 if it's not significant?
Yeah, it's just, for this particular question, I wanted one non-significant variable in there and no reason for it other than, but what Taylor said is right. If I was settling on what my best model would be, I would take out the other variable as well. Is it all fitting? I want to get it so all the blanks I need to write on are on the screen.
Yeah.
Okay. So H, I've scrolled past it, but H was not significant, right?
No.
And its p-value in the model is not significant as well. So, you know, you could pull it out of the model. But. All right. Any questions about how to fill any of this stuff in?
What is the degree of frequency for the model? Is it 4 or 5? Or degrees of freedom?
It's the sum of the numbers for the x variables. So it'd be 3.
Yeah, see, I used 4 because of the one before. I had 4 of them, but then I noticed they ran.
Yeah.
But I left all my numbers the same, so I don't want to go back and change.
So when we do look at this, only look at the bottom part because the top part has ST, AT, H, and EVAP.
Well, EVAP is the one that they add.
Where are you
right?
seeing that?
is the one.
Because he said that it adds a line.
Yeah, this evap is the y variable.
Oh.
Because it adds the.
Yeah, so what it says here, if you read what SAS says, x prime x inverse, parameter estimates, and SSE. So it's got an extra row for the dependent variable and an extra column for the dependent variable. So these are your parameter estimates. So look at these numbers. Negative 58, 0.2, negative 0.32. That's these values, right? And then SSE, 45, 47.96, 45, 47.96. So it's just adding those because sometimes you want those values also, so it's a way for SAS to give you those values into a matrix you can work with. But they really have nothing to do with the x prime x inverse matrix.
So then AT's standard error would be, oh wait, hold on, that's not right.
And then just root MSC times 0.0002076098.
Yeah, if you go AT over to AT column, there's your diagonal, right? So the standard error down here for AT is going to be that value right there times the mean squared error, which we have to compute, and then the square root of all that. Right? So you have to take this. It's not this number times root mean squared error. It's the square root of this number times root mean squared error. Right? These are variances in this matrix. So what I always do is I take the mean squared error, I multiply by that, and then I take the square root of my answer, and that's your standard error. Okay?
And mean square error is the error is the sum is the SSE divided by the DFE, right? Which in this case is 42. Is that right?
Well, I kind of got lost what you were saying.
Sorry.
The MSE is, what'd you say?
The SSE
Oh,
divided by the DFE.
right.
Okay.
So if we get, let's go ahead and just do this. What's my my total degrees of freedom?
45.
45, because it tells us that we had 46 observations. So this will be 45, leaving how much for error? 42. So then sum the squared error divided by degrees of freedom for error. Take 45, 47.96, divide by 42. What do you get?
You get 108.2847883.
Okay, and that's a lot of decimal places of accuracy, but to stay accurate in the later calculations, it's good to keep a lot of places. How would I get the total sum of squares? You just add the ones up here.
And that's, you want the.
Yeah, you start reading me numbers.
It's 9642.10869.
Okay. And then mean squared error, or mean squared model.
Is 1698.049193.
049 what?
193.
193. Okay. And you get that number.
By dividing the sum square model by the DF, the DFM, okay.
Right? So 5094 divided by 3 gives you 1698. Right? And then F value,
This is mean, those two divided.
divide these two. So 1698 divided by 108.
15.6813.
Okay, 15.6813. And a p-value.
So we do the F. Yes.
Okay, you go FCDF on your TI-84 from that number, 15.6813, comma, infinity, comma,
342.
we have degrees of freedom for numerator, which is 3, and degrees of freedom for denominator, which is 42.
5.467 equals the -7.
So very small p-value. And you can look at the r-square value and realize that, yeah, you're going to have a really small p-value there because this p-value applies to r-squared as well. It's also a hypothesis test for whether r is 0. So what is r-squared?
R squared is the square root of this.
You're going to take the mean, or the sum of squares for model, divide by sum of squares total. So 5094 divided by 9642, and what do you get?
You get 0.5283229.
That's probably enough. Right? I was actually expecting a bigger number than that because of how significant that p-value was. But remember, the p-value is only checking to see if that's 0. And I guess this is a long ways from 0, even though it's not that close to 1. Okay, and then adjusted r-square, we already kind of worked through one of those. So it's 1 minus 108 divided by the mean square total. Or you can use the formula they give you in the book, which I can never remember because it's got a lot of stuff in it. But it's the same thing.
So, sorry, 108 divided by the total.
By the mean square total, which we don't have written here. But this 9642 divided by 45 would be mean square total. And then you take 1 minus 108 over that mean square total. And that'd be your adjusted r squared.
It's 0.4946.
And the r squared was 1 minus the MSE over the the MSM over the MSE. Is that
Nope, for r squared it's SS's, not MS's. Right, so
That's
r
right.
squared is SS model over SST, which is also 1 minus SSE over SST. So that's how I remember the adjusted r squared. You take this form of it, but you replace it with mean squares instead of sum squares. Okay? And then root mean squared error would be the square root of 108, which is going to be 10 point something.
10.406.
Okay? So now we're ready to come down here and do this line, the standard error of AT. So I'll write that here, standard error of the variable AT, which would be B sub AT. I'll write it like that, rather than B sub 1, B sub 2, or whatever. Just B sub AT. The standard error of that is going to be the root mean squared error, which is 10.406 times the square root of, we've already pointed at it, but
So it's when AT and AT line up?
right, it's the diagonal element corresponding to AT. So 0.30 and 2, and then 0.76.
So the mean squared error times the variance of that parameter, the square root of the parameter, or the square root of the parameter.
Yeah.
Oh, so
So you could take mean squared error times that number, and then take the square root of your answer. Or you can do the square root of the mean square error first, and the square root of this thing first, and multiply them together. It's easier, I think, to do it. Yep.
Alright, do you wanna write it down?
Sure.
It's 0.1499.
Okay. Which looks good. It's kind of a check when you have this one, you're kind of saying, well, it's in the ballpark of that one, so that's probably right. If you were magnitudes of order different, then you might start wondering, did I do that right? It's not a guarantee, but it's kind of a good check. Okay, and then the t-value, estimate divided by standard error. And so 0.32 divided by 0.15 is going to be 2.15917. And that p-value is kind of interesting. That's going to be a borderline p-value, isn't it?
I think it's still significant.
Should be within. But you do the TCDF.
What I messed up on was
PCDF from that value to infinity,
times 2.
and then times 2. That's the part most people forget, including me. So from there up to 9999,
The degrees of freedom.
and the degrees of freedom for 42. And then you got to multiply that times 2 because that's going to be a one-tailed p-value. You need a two-tailed p-value.
It's gonna be 0.036552.
0.36. Say it again.
552.
552. Good luck. So that one is significant. It's kind of borderline. 0.05 would be the border. So it's kind of borderline. And I looked at that number. That's not very much bigger than 2. So it's going to be around 2 for the t distribution is where you start to get close to significant. And it depends on degrees of freedom as to how much bigger than 2 you have to get. If it were infinite degrees of freedom, then you'd have to get to 1.96. Okay, only one thing left. 95% confidence limits on that parameter. Not that parameter, this parameter.
This will be your parameter.
Okay? So this is the parameter estimate, which is 0.32374 plus or minus
T-value, T-crit.
T crit, and you were gonna put that number there, weren't you?
Yeah, I was learning to.
Yeah, I was gonna slap you. That's a very common mistake, and people that I know better. But you get in the heat of the battle on a test, and you, oh, I need the t value. Oh, there's the t value, and you write it, but it's different. This is t test statistic. This is t critical value. This you get from a t-table or your inverse t function on your calculator.
And it would still be using degrees of freedom error.
Still 43. So basically, this t critical value is the cutoff for when this is significant, right? So we're going to get a number that's just slightly less than 2.15 something.
2.01808.
So it's 0.18. So 3 decimal places is plenty for that. Okay? And then times the standard error that we already computed. So 0.1499. Okay? What'd you say, Anton?
0.0223 to 0.62625.
Okay.
You know, as much as I had significant digits shoved down my throat in high school, We don't really use them all that
Take chemistry.
Yeah, you know,
much. But it was in math classes.
in statistics, I had a lot of science and pure mathematics before I went to grad school in statistics, and statisticians take a different attitude towards all that. It's more like, you know, how accurate do you need to be here, right? And it depends on what it is you're measuring. If you're measuring incomes and they're measured to the nearest $1,000, then having it out to 5 decimal places is no help at all. But if you have values that are all, you know, 0.000 before the first digit, then you need a lot of places. So you just kind of use some common sense. Okay? Now, I'm not sure I've said this before, but what do you notice is different about the confidence interval we just computed and the other ones? The other two include 0. And the other two have non-significant p-values. So if the confidence interval excludes 0, then you say, I have sufficient evidence to say it's not 0. The p-value should support that. Right? So if you ever notice that, hey, my p-value isn't matching what my confidence interval is doing, then you know you made a mistake somewhere. Okay, that was a lot of fun.
We get to do it all over.
Okay, number 7 says, refer to that previous one, give the null and alternative and conclusion of the F test for model. So the F test for model, we already had a question about that, but we can write it out instead of 1s and 2s, we could say beta sub, I already forgot, ST is equal to beta sub AT is equal to beta sub H is all equal 0. So there's your null. And to me, this is fine to put those, or it would also be fine to put beta sub 1, beta sub 2, beta sub 3. And 1, 2, 3 is probably easier to write, but it's harder for me to remember what it is. And then what's the alternative?
We just write,
One of those is non-zero.
yeah.
At least
And you're fine if we just write out just
one
English.
Beta is
What
not
was
zero.
is not 0.
And
That's good enough.
So the arrow is fine.
Yeah, even the arrow's fine. I don't get too picky about stuff like that. If I can tell that, yeah, they know the answer, then great. But I know some instructors that will take points off if you don't put your name in the right spot on the thing, you know, and they're trying to teach you to follow instructions, and there's validity to that, but I'll let them worry about that. I'll test what you know. All right, so now conclusion. What's that? We reject the null hypothesis because that p-value was really small. It was something times 10 to the negative 7th. It's on, you know, I've erased it, but it was on the previous page. But it had a really small p-value, so you're going to reject the null, and that's not enough. You can't just say the conclusion is I reject the null. You have to say what that means. You have to explain it to your mother. What does that mean?
At least one of the betas is not equal to 0.
Yeah, and my mother would say, beta? What the heck is beta?
Slopes of the line.
At least one of the variables, and you could even write it, I wouldn't expect you to, but you could say the variables S, T, A, T, and H, at least one of those variables is a significant predictor. Or you could even say a good predictor of evaporation.
So, because it's, even though our R value was like low, it's saying it's significant as far as the things we've considered, right? That's what the model is.
That's
in the
right.
end, being 50% correct is really not that great, but
Yeah, 50% is not that great, but if you've got a lot of variability, And, you know, there can be a lot of error, but you're still explaining half of the variability in evaporation, right? So it's a lot more than zero. That's what that p-value says. You're doing better than you could do if you just said, oh, all days are going to be the same. Okay, then B is on the bar here. A test for significance of AT given ST and H are already controlled for.
Those are just the t-tests, right?
Those are just the t-tests. That's what those t-tests are. Given the other variables have already been controlled for, now how much variability does AT explain?
So that's underneath the parameter estimates.
Well, it's on the line of the parameters.
Yeah, like so intercept.
Yeah. So I've erased it, but it's this line that we computed a minute ago, right?
Yeah, I'll list it on there.
So it's the one that we use,
It's got this down there.
0.149.
All right. So what's the conclusion?
It's significant at a alpha 0.05.
Isn't that? It was significant. Give the null alternative and conclusion. The null is just that, right? Because beta is the coefficient beta has been computed as after adjusting for the other variables. Here's the beta we need for this variable. So it's already. Well, the null would have the beta, but the lowercase b is the estimate of that. Okay? So you would reject the null.
The wording is we would say that AT is a significant predictor.
Right. We would say that the variable AT does help predict Y even after you've controlled for ST and H. And AT is atmospheric temperature, and ST was soil temperature, and H was humidity. So after we've explained everything we could by what the soil temperature is and by what the air humidity is, knowing the temperature of the air still helps us explain variability in the Y. In fact, it's the best predictor because that's the one that is significant in the model. The others were not. Okay, so let's see, top row of this table. Fill in the blanks of the first observation below and the missing hat value in the second observation. So we need a predicted value. How do we get a predicted value?
Sub it all that edge.
What did you say?
Sub it on your
Yep.
model.
They gave you the values for the x variables right there. So you go back to the model, use the parameter estimates. So we have an intercept, so y hat will be negative 58.58968 plus 0.20536 times, and I scrolled so I didn't write it down. What was the value for soil temperature?
Oh, 147.
Really?
No, 80 was
The air temperature is 147.
That's what I'm thinking. What's the...
No, AT is 151,
Why is
which is a lot worse.
So apparently they're measuring on some scale that
Kelvin.
Kelvin or
It can't
something.
even be Kelvin. That's still insane.
Yeah.
It's still really
that would
cold.
be negative. That would be way negative.
Yeah, so 147
No, 147 is S2.
was what? The first part?
That's
Okay,
apparently
so-
they're on Mars or something. They're trying to measure that.
It's measured in miles per day.
What'd you
Soil
say?
temperature is pretty real.
Or wait, no, that's wind. Never mind.
It's measured in
If
what?
you're going low enough.
Never mind. It said wind was measured in miles per day.
Oh.
That's what's off.
And so they don't say what the scale is on temperature?
It just says
Average.
for that day.
Okay, well, probably it's either Kelvin or it's a
Kelvin
been
does not
rescaled
use-
somehow, right? It's like, well, I need to rescale these values so that, sometimes we do that in regression because if values are too close together and there's not very much variability, you scale them up so that you see more variability between them.
Place up in my screen.
Yeah.
Hear about the guy that got absolute zero? No, he's okay now. He's 0 Kelvin, okay.
So it's saying it's like negative 6 degrees Celsius.
The hand wave of dismissal.
Yeah, I'll have to check on that value because that came out of an old textbook that I've used, so I can look it up and see what those were measured in. But anyway, for this problem, it's 147, right? And then, so then plus 0.32373 times 151, and then minus 0.00986 times 398. Okay, so when you multiply all of that out, what do you get?
16.5587.
16.5587. Okay?
How's humidity 398?
Well, like I said, I don't know the scales on these things, but they've apparently rescaled these. And scientists do that a lot. You know, they have an instrument that, you know, it might mean 39.8% humidity or whatever. And they've just moved the decimal and rescaled things. You know, they do that a lot.
Yeah, I think it would be decimal and everything. That'd make more sense.
Well, I mean, it'd make everything even smaller decimals on your model. Right? What they should be.
It's like 14.7 degrees Celsius actually.
Yeah, 14 degrees Celsius would be livable.
147, I have other issues besides evaporation.
Okay, so that number 16.5587 would go in here, right? And then residual.
Residual is just
The actual value minus the predicted value. So that's going to be about 14 something,
13.4413.
13.4413. Okay. And then standard error of the mean predicted value.
Yeah, how'd you get to 13 point?
Take the actual value minus
30
the-
minus whatever you got for your
Yeah, it's just y minus y hat.
The 30's given to you right
Here's
there.
my y.
Oh, okay.
Okay. Now the standard error of the mean, that one's a little bit tricky to get. And obviously, since I left it on that row, you need the hat value. What is the hat value? What's the name our book uses?
It's the
The
distance.
distance factor. So you need the distance factor. So the standard error of the mean predicted is what? What's the formula for it?
Root MSC
Okay, root MSE.
is the square root of that hat value.
Yeah, of the distance value. And so that root mean squared error we had on previous slide or previous page, what was the, anybody have that?
It's 10.046.
Okay, and then the square root of the distance value, and the distance value is 0.11046.
So the hat value is the exact same thing as the distance value.
Yep.
Okay, good. Just
That gives you 0.3323. Oh, sorry, I need to times that by the 10.
the root MSE is 10.406.
406.
Yeah.
Okay.
3.4584. I think you were on the last one to 5.
Okay. Looking at the other standard errors that are below that, I'm thinking, yeah, it's in the ballpark. That's if we had got 3 point something and these were all 30 point something, and say, oh, I've got something wrong. But Okay, and then confidence limits. I think let's save the time and not do those, but how do you do them?
It's just your
You figure out your T critical value, multiply by the standard error you just computed,
You're
and
still
then,
using the error degrees of freedom, right?
right, still error degrees of freedom.
Would we do a 95%?
Yeah, does it not say? When in doubt, you always do 95%. If I forget to say, and I do half the time, and that's the default in SAS, so that's what these are.
And what's the standard error of the individual?
Yeah, now that's a good question. Standard error of individual.
It's one plus the distance value. That's for
The only difference is it's 1 plus the distance under that second square root.
Yes.
And then we've got back solve that half value at the end at the second one.
What's that?
Don't you just have to back solve that half value?
Oh, quit cheating. Yeah, it would work. It's not what I wanted you to do.
What do you want us to do?
Because you're doing the same thing as that they had you do on that one homework problem. You could back solve from these confidence intervals to figure out, or from the standard error. You could back solve from the standard error to figure out what that missing half value is. But
What's the preferred way?
Yeah, what would you
You would
prefer us to
need
do?
matrices, wouldn't you?
yeah, you need, which is, I think we gave it, didn't we?
I
Yeah,
think so.
yeah, that was the thing, the diagonals, right?
Yeah.
Of your half values.
So there's the x prime x inverse matrix, but then you have to make a vector out of the values of the x's, right, for the value you want. Multiply by that. Right.
Let's back solve.
Yeah, it's a whole lot harder.
Okay, so which one? How do you do it? Now I heard two different versions and now I'm confused.
Unless you give us a matrix.
So you're gonna give us a matrix, you asked to find the half value, right?
Be prepared for that. If I make it possible to back solve, then whatever, do it. I mean, it's there. But
It's math. One way.
But I could also say, here's an x prime x inverse matrix. Give the predicted value, and here's a model. Give the predicted value for these values of the x variables. And then I could say, what's the hat value for that? And then you'd have to use the matrix. So if I did that, how would you get it? Here's the vector of x values. So that is x sub 0 prime. Right? So x 0 with no prime is the column vector with those same values. And then you take x 0 prime times x prime x inverse without the sub 0, and then x sub 0, and that would be your half value.
So for the x,
We would have to type in this whole.
well, the x vector, we just use the value. Well, for the x prime.
Yeah, this is that x prime x inverse matrix that was up
Oh.
the top part.
So would you leave off the last column?
Yeah, they aren't part of the x prime x inverse matrix.
Okay, so you would leave off the eval.
Right. So in the SAS output, they added the extra column and the extra row, so you just use just the part that's above that. But to be honest, this was actually a test question that I've used in the past, and then I made it onto review. And I'm sure I was expecting them to back solve because, man, look at the numbers that are in that x prime x inverse. How long would it take you to enter that matrix into your calculator? You know, so it would eat up an awful lot of time.
I don't think we did a lot of this matrixing stuff.
No, when you came through, we didn't do as much with matrices.
Except the back solve.
Okay, so everybody understand, we didn't go ahead and fill in the numbers, but they'll be in the key once I get that posted, if you want to check your work. But everybody understand how to get them? Does everybody understand how you would back solve this for the distance value? If you're given the standard error, you know the root mean squared error.
So like your standard error, just square it.
Square it, and you got it. All right, so let's see. Is everybody done with this? Let's see. Yeah, we probably want to talk about that one. It says a study was done to determine predictors of mobility among adults. The variables considered are distance y, that can be walked in 3 minutes, the flexibility x1, and as measured by a spreadsheet test, and then age category. Now, I originally had this on the review as age had 3 categories, but then we didn't quite get done with that section, so I said, well, so I modified this to just be young and old. So 70 or less is young. Keep that in mind. And then older than 70 is old. All right, so define a multiple regression model that uses dummy variables to include the categorical variable age and allows for different intercepts and different slopes. Write out the model using betas, etc. So y hat equals, I'll help you get started, beta 0.
You're so generous.
Beta 1
Plus beta 1,
X million.
okay, and x1 is flexibility,
Plus beta 2x.
okay, but what is x2?
That would be the dummy variable of age. So 0.
Okay, so instead of calling it x2, we try to denote that it's a dummy variable somehow, so we use different symbols. The book uses D for dummy, right? So it'll do D1 or whatever. Let's say D sub A for the age dummy variable. And then you have to define that dummy variable. So dA is equal, you have to explain to me what that variable is.
So under 70 is 0.
Okay, so D sub A will be 0 if age is less than 70. No, it's 70 or less. So less than or equal to 70. Right? And then it's a 1 otherwise. Okay? Now we're not quite done. It says the variable, or what am I doing? Allows for different intercepts and different slopes. Does this allow for different intercepts and different slopes?
Need interaction.
We need interaction. This allows for different intercepts, but not different slopes. So we need an interaction term plus beta 3 times x1 times dA. And that will allow for different slopes as well.
Spreadsheet on X1.
No, I just
So
got
that's
some
all you have
clutter
to
there.
do to make it allow for different intercepts and slopes.
Yeah.
Just add another one.
Because it's not okay. DA is 1.
This is the interaction between x. You have to have that product term to let the slopes change. This one lets the intercepts change, but not the slopes.
Yeah. That's the.
Okay, now in your model, explain who the reference group of subjects are. People that are less than or equal to 70. Right? Now technically it's more than that, but that's all I'd be looking for. It's always, when I ask that question, it's in reference to your dummy variables or your categorical variables. But also the reference group are the people that have the intercept, right?
So if we were to flip, we would got the 0 for those for your DA.
Right.
Is that good?
But it would also technically be people who were less than 70 and had 0 flexibility, right? So it's when all of the x variables are 0. That's your reference group. Beta represents your reference group, right? But when they ask that question, it's always just with respect to the dummy variable.
So really, it's who has zero flexibility whatsoever. Is that even possible? Like, you can't move.
No, that's an actual test, a flexibility score. They have these tests, and you can get a 0 on that without being
Doesn't mean it's
stiff like a board,
Mine was pretty
but-
low in high school.
but you're not touching your toes.
Mine was not very flexible.
Okay, so part C, would you expect there to be an interaction between age and flexibility? So this is just kind of a concept question, an intuition question, right? Would you expect to see interaction? Well, what does interaction mean? It means the effect of flexibility would be different for young people than for old people. Think of it in terms of the ability of the variable flexibility to predict y. I forgot what y is.
Distance.
The distance you can walk in 3 minutes. So it's called a 3-minute walk test, right? And if they're young, even if they're not very flexible, they might be able to walk pretty well. So pretty much everybody hits, a max distance in that 3 minutes or whatever. But as they get older, then the flexibility becomes more important. And so the effect of flexibility is different for young people than it is for old. And I would say, yeah, I would expect there to be an interaction between those groups.
For the why or why not,
I just said, oh, that's right, everything I just said. But, yeah, for somebody who's young, that question actually makes a little more intuitive sense the way I had originally had it with 3 age categories. And I had a category that was like less than 50 years old. And most 50-year-olds, unless there's some kind of a physical abnormality, don't have any problem walking for 3 minutes. Right? So flexibility isn't going to get factored into it. But flexibility becomes important as they get older. All right, so what about number 9? What are we asking? Computational formula for the coefficient of determination. Let me scroll that up a little ways. Oh yeah, this is the proof question. Okay. So, what is the computational formula for r squared? Not adjusted r squared, but r squared. R squared is SSM over SST, which is 1 minus SSE over SST, right? Now, how do you compute SSE and SST? The sum of the residuals is yi minus y hat I, right? Sum of squared residuals. Oh, I'm going too far here. Well, no, that's okay. This is fine. I thought, what my mind was thinking my next step was going to be a lot more than I'm going to need. So, but then on the bottom, this is sum of, what's sum of squares total? Is it a y bar? yi minus y bar squared, right? Now, if I take this thing on the bottom and I divide by n minus 1, what do I get? Sy squared. So if I divide this by n minus 1 and also multiply it by n minus 1, I haven't changed it. I've multiplied by 1. But then I've made the bottom of this n minus 1 times sy squared. And now what about the top? So I'm almost there.
Same thing.
Same idea. If I divide this by n minus 2 and multiply it by n minus 2, I haven't changed it, but this is then the estimate of the variance of the errors. So it's SE squared.
And we get the n minus 2 because we're assuming it's a linear model.
Right. It says a simple linear regression model. So you know that the error degrees of freedom would be n minus 2. But if I could ask the exact same question and say, consider fitting a multiple regression model with 3 x variables. Then you just adjust the n minus whatever that you divide by and multiply by, and that's still your estimate of. Right? But this would no longer be n minus 2. That's too easy of a proof. I would have to give you guys a lot harder one.
That one's hard.
There's no way I remember that.
Okay, there's some kind of concept questions here about quadratic regression. Here's this one. This is an actual example I found in a different book. And it kind of cracked me up at first, but I thought, you know, that's kind of a good point. But let me scroll just a little bit there. So we have a construction of a linear regression model for an engineering problem. And engineers, man, you know what they're like. Cell data that relates a known load to applied to a load cell to the deflection of the cell. Basically, it's if they put a load on this thing, how much does it bend? Right? What's the deflection? Right? And so then the model is then used to calibrate future cell readings, blah, blah, blah. So the following plot shows deflection as the response variable and load as the predictor variable. Does it appear the model fits the data well? Really well, right? Look at R squared.
Pretty good. Hey.
To 4 decimal places, it's 1, right? So it's doing a pretty good job. So linear model does pretty good. But can we do any better?
Sure.
This is the residual plot from that model. What are you supposed to see in a residual plot? Shotgun blast, right? Or at least random scatter, horizontal stretched out across there, right? But you see a pattern here. And you see a curved pattern, a quadratic looking pattern, right? Yeah.
Are those residuals, that residual plot, did they like blow it up a little bit because they?
Exactly. Look, you can't read it from where you're at, but this says studentized residual without, can't read it either. Without current observation. Yeah, there you go. Without current observation. We'll talk about these in chapter 5. But basically, the studentized means it's been standardized. So these are like z-scores, right? So this is like 2.5 standard errors away from 0 and so on, right? Which expands it so you can see the pattern. If we just plotted it in the units that were on the previous, you would see the same picture, but it would be, you know, like that. So obviously there's curvature in the residuals that's not being accounted for in the model. So what's the better models? We need a quadratic model. So the previous question says, are there any violations to the assumptions? And you'd say, no, it looks fine. It looks like it fits amazingly well. But now, do you see any problem? Yeah, now I see a problem. I see that there's curvature in this data that we have not accounted for. And then,
Well, I have a question.
yeah.
Why would we, I understand that it violates it, but why does that mean that we need to have a quadratic formula now? If what we were trying to predict in the first one is perfect.
It's not perfect. Here's the residuals. So it isn't perfect. If it was perfect, the residuals would all be zero, right?
Oh, yeah.
So the thing is, and it's kind of what cracked me up about this problem is, how good do you have to be? But, you know, if you're talking about, you know, something that they're keeping accuracy to 10 decimal places and the decimal places are important, then maybe, you know, having this instrument off or deflecting a little too far or whatever, it's a big deal. So just because linear, it's almost perfectly linear, these might be important. So that's what I thought was kind of funny about this problem. But okay, so now what would you suggest the model be? A quadratic model instead of a linear model. So I think that's all I did on that problem. Or no, I did. Here we go. So this plot is studentized, deleted residuals. You don't know what those are yet, but we'll do it in chapter 5. But basically, here's a residual plot after I fit a quadratic model, and that looks much better. There's no pattern to those. And then this is a normal probability plot.
So there's no violations to that?
Yeah, no violations there. Normal probability plot should look like what?
Kind of a bell shoot. Well, not really.
Look linear,
It should look linear. It should follow that blue line. The point should follow the blue line. Because remember, what you're plotting is percentiles from a normal distribution versus the actual percentiles in your data. And if the data meaning the residuals. So if the residuals are normally distributed, then those percentiles or quantiles should match up. So they should be on a line that's y equal x.
So, just up here, so part B, you're just saying, when it says, instead of suggest a remedy for analysis, you just want us to say, use a quadratic.
Yeah, fit a quadratic model. The other option would be to do a transformation, like a square root transformation or something. So that'd be another thing to try. But. Okay, well, as I was making this thing out, I was running out of time, so I didn't type up that question and put it in here or find a similar one with other data. But this exercise, I'm running out of time, so we won't have time to do it. But this exercise 414, you had a homework problem 413, which is very similar to that. So as long as you can work that, it basically gives you some SAS output from a quadratic model and asks you questions about it.
And for the test, we get one sheet, right?
One sheet.
I always gotta make sure, because they're different, front and back, or,
Front and back.
sorry, it's
one ream of notebook.
One
You
ream.
get your text.
Ream is
One? I get one whole ream? So that's that problem. Let's see, is there more?
Yeah, page 6.
Oh yeah, this one is. Okay, so this one talks about another dummy variable type problem with an interaction term in it. We've got dummy variable, the categorical variable has two levels, so location A and location B. And it shows how the dummy variable is set up. So z equals 0 is location A, z equal 1 is location B. Determine the least squares line of y on x separately for location A and location B. And all I gave you down here at the bottom is the regression output of the model that had the dummy variable and the interaction in it. So what is the model for location A?
You would leave out B2, B0 equals B1x plus E, right?
Okay. For location A, z is equal to 0. So y hat is equal to
Beta 0 plus beta 1x.
beta 0 plus beta 1x times 0 times this number times 0 times this number. So that's it. So all I got to do is fill in the numbers. I've got 2.00856 minus 0.03915x. There's my model for location A. So what's my model for location B? This time z is a 1.
Y hat equals beta 0 plus beta 1 x plus beta 2 z plus beta 3 x z.
So beta 1x plus beta 2 times z, but what is z? Z is a 1, so plus beta 2
Oh, plus.
plus
Plus B3X.
beta 3x. Now I can combine like terms.
So you do beta 0 plus beta 2 plus beta 1 plus beta 3x.
And now I fill in numbers. So this is beta 0, 2.0086 minus 2.42792. Okay, somebody do that one on the calculator, and then the rest of you do the next one, which is negative 0.03915 plus 0.19506.
The first one is negative 0.41926.
41926. 36.
And the second one is 0.1559.
0.19, say it again.
0.155.
155.
And no. 91.
91.
The first one is no 2. It was just 9 pieces.
Got it?
Okay, what about B?
So to answer that, you have two models. You have this model and you have this model. Right? Okay, we're out of time, so I won't keep going, but I'll get the key posted out there. The key may not be there until tomorrow afternoon because I got something else I got to get done by noon tomorrow, and it's going to take me more hours than that. What?
Explain B real quick.
Okay, provide an interpretation for the, the parameters for z and xz. So that's,
Talking about betas, right?
So that's,
right.
So
So what is the interpretation of beta 2?
if it's location.
It's the change in intercept when you change from location A to location B.
Everything else is constant, right?
And XC is a change in slope.
Well, no, you don't have to hold x, it's just the change in the intercept of the model
and then the next one's
for location A versus location B.
And XC is a change in slope.
And the other one is the change in the slope. Right?
So.
And you can see that directly from here. Right, this one has intercept of beta 0, this one has intercept of beta 0 plus something, so that something is the change in the intercept. All right. Well, good luck. We will see you Monday.